For those of you who don't know me, I'm a postdoc as of this past fall at the Harvard Smithsonian Center for Astrophysics. And my research primarily focuses on radio transients and emission from various giant space explosions, basically, and their shock waves. And today I'm going to tell you about the research I've been working on since I started my postdoc, which is on the tidal disruption event Swift J1644+57. So a little bit of background for those of you who aren't familiar with this object. Swift J1644+57 was discovered by the Swift satellite on March 28th, 2011. And they saw there's basically a huge source suddenly of gamma rays, X-rays, a lot of multi-frequency radiation coming out of this galaxy at a redshift of 0.354. And multi-frequency observations at that time indicated that this was basically a star went too close to a supermassive black hole that was previously dormant at the center of its galaxy. It became tidally disrupted, so it got ripped apart, and it launched an on-axis relativistic jet directly toward us. This was very exciting at the time because nobody had really predicted that this relativistic jet could happen if a star became tidally disrupted. It was sort of the first real studied TDE in any detail. There were two other, I should mention, on-axis relativistic ones discovered in 2011, but they were much, much further. There haven't been any seen since. There's been to date maybe about 100 TDEs, which we know of. Less than 10 of those are detectable in the radio. And so right now we think maybe 1% of these have relativistic jets or something like that. We really don't know. There's still a lot of questions we don't have. But this is a very exciting object because we've had such great samples in all sorts of frequencies studying it, what goes on when this relativistic jet happens during a TDE. So what we also saw, though, while observing this object, was around day 500, as I said, this relativistic jet got launched, and also then about a year and a half after, the jet actually turned off. So what you can see here, if I bring my mouse over, this is X-ray data from Swift. You can see these variations. This is thought to be basically because you had the star became unbound, of course, as it got ripped apart by this black hole. But bits of it, went outside of the tidal radius and kept falling onto the black hole and fueling this jet. But then what you end up seeing is after about 1.5 years, you see these data points here really suddenly sharply decrease. This is in Zouderud et al. 2013 was the paper. The black square point was actually the Chandra observation. So after, at the latest point, we have a lot more Chandra data for what's going on with this object. And what you can see here, this blue line is, so if you take synchrotron emission from radio, and I'll explain how we do this in a bit, you can estimate the flux density that you'd see in X-ray just from the forward shock emission as you have the synchrotron going outward, so not from a relativistic jet. And you could see that the latest X-ray data really hit exactly what the predictions are based off of that synchrotron emission. So people interpreted this as the jet had turned off. And this is also very exciting because there's a lot we don't know, of course, about relativistic jets from supermassive black holes. But we do know they last for, much longer usually than a year and a half. So it's very exciting that you have a relativistic jet where you can study the entire thing and what exactly has happened with it and things like that. So as I said, I was going to tell you a bit about how we use the radio data to do things like predict in X-ray what sort of emission you should have from the forward shock. So the thing to know about these outflows, whenever you have outflows in radio from gigantic space explosions, and which TDEs definitely are one, is these outflows generate synchrotron emissions. So this is just electrons spiraling in magnetic fields, and this is what we study in the radio. What you get, though, if you're taking frequent observations at multiple frequencies, so we've been doing this with the Very Large Array in New Mexico for this object ever since it was first detected. You basically can do multi-frequency observations, get what's called the spectral index distribution, or SED, and it has different breaks in it, which are very well modeled and very well understood from basically GRB physics and things like that. So we can basically model the synchrotron emission over time. This curve will shift as the synchrotron emission evolves. It's going to, for example, the peak will go to lower and lower frequencies. And what you can do then with this model is actually obtain various parameters from physics from understanding your SED very well. So for example, you can understand the radius that the shockwave's at, the energy in the shockwave, the density, and you can also actually learn a bit about the shock physics if you take this curve all the way down, to the X-ray regime. For example, you can study shock physics, so the magnetic field energy density, the electromagnetic field energy density, all sorts of things you can really study from basically just the radio SED. So to show you what these guys look like, we've been monitoring, as I said, this object in the radio. And the first thing I should say is that it is still observable. A lot of people think of the relativistic jet phase, but it's definitely still out there and it's still expanding outward, and you can study this in the radio. The last update was Eftekari 2018. It became non-relativistic at 700 days, was one of the main findings of that paper, and the emission is dominated by the forward shock expanding outward now, interacting with the environment basically in this galaxy. So what we did was we basically have the most recent radio observations, and we also took Chandra data at days 2493 and 2795 post-explosion. I looked it up for those interested in this trivia. Today is day 3430. So the most recent observation was November 2018 or so. We basically did get these detections, and as you can see, we did fit the SED, as that I was just describing before, to this, and you still have this, very nice curve. I should note that the reason this curve has much more variance is this here, if you look, is unfortunately an upper limit. That is the L-band observation in the VLA, which those who know their radio know can have a lot of radio frequency interference, so it's a very noisy observation. Unfortunately, we couldn't constrain that point in the light curve. So we just have bigger error bars on it. We can still use it. The other cool radio observation, though, we got as a bit of a bonus this time around, was actually from the Very Large Array Sky Survey. So for those not familiar with VLAS, as it's called, it's sort of the first big radio sky survey in about 2 decades with the VLA to look at the entire sky and see what's going on. And a lot of people are looking for transients in VLAS, including various TDEs. And we did take a look, and we did get a detection of Swift J1644+57, which is this data point right here. Of course, the error bars are bigger than a dedicated observation, but it's really nice, of course, to have a bonus observation. If we use it, we can also put it together with our other data points. The luminosity, as I said, it's currently fading basically as you expect for non-relativistic TDE. Oh, I should mention, most of the analysis I'm going to talk about, sorry, I should have mentioned this earlier, is after 700 days. So when we're in this non-relativistic phase, because it's very different from the earlier phase for this object. And yeah, so I just wanted to mention this for anybody out there listening who's studying TDs and trying to find them in VLAS. I can tell you there's at least one in there, so that's always nice. So to continue on, though, with the analysis that we did here with this most recent data. So as I said, we have these curves we're fitting for synchrotron emission, and basically the steepness of the curve is called P, which is basically the value for the energy index, and it depends on the particle acceleration. And it was previously measured in the very early days of Swift J1644+57 as 2.5. P equals 2.5 was what it was measured as. As you can see, though, that initial data, there's a lot of errors on P. So if you basically just take model, run NCMC, and simulate what are the best fits for the steepness of the curve based off of the model. I did this basically for all the different observations. What you can see is P equals 3 is actually more accurate, especially after 700 days. The reason this is interesting is most models of these blast waves, when you model them for the SED, you don't really assume that P is changing very much over time. I don't think anybody's really done an analysis like this. It's also not clear to me from just looking at this data what's going on these earlier days. Is P physically changing? Obviously, if we get more data points, maybe we'll notice something more. It's really too early to say, I think, but we can definitely say that after 700 days, it's definitely a P equals 3 value. So that's what we're gonna run with. And maybe, if we find another on-axis relativistic TDE, we can see if P changes or anything like that in those. Unfortunately, I checked and you can't order them on Amazon, so we'll have to wait and see when we find another one. But of course, if you update your parameter, like the steepness of your curve, you also get to redo all the data analysis again to see what's going on. As I said, modeling the spectral breaks in this SED and finding things like the peak frequency and the peak flux and things like that. What we can see is, obviously these values all shift, but the trends in the data are very similar, so pretty confident about the reanalysis there. And what we can then do is study the evolution of the outflow and what is actually happening at this TDE. So if we're, as I said, looking after day 700 or so when it's non-relativistic, this is what we're focusing on here. And extracted from those SAD values, we're using Duran et al. 2013 for the equipartition analysis to figure this out. And we obtained the radius of the shock wave, the energy, the co-moving magnetic field strength, the total number of radiating electrons in the emitting region, and then from that, the density, if we assume certain things about the size of the emitting region. I can tell you these parameters are consistent with Newtonian expansion. So as I said, this is a very late time evolving object by this stage. What we can see is the radius, as I said, if I redo this, it's expanding a bit, but not very much by this point. I mean, it's definitely nowhere near the initial relativistic jet days. The energy is also decreasing at this stage, as we can expect. The magnetic field strength did not fit on this plot, but I can tell you that's also decreasing. But then what we can also do is look at the density around this object. And so this is basically, if we're taking the radius versus the density, you can then basically say, okay, what is the density around this galaxy of z equals 0.3, which is really amazing if you think about it at these later distances. So what we can see here is it's from about 0.5 to 1 cubic centimeter, which is consistent with an ISM surrounding this galaxy. Just for comparison's sake, this is the same data plotted with lines for the data we have for M87 star, or for the region around M87, and then the region around the center of our own galaxy, around Sag A star. The first thing I should note, which I think is kind of incredible if you think about it, we actually know the density environment around this galaxy very far away much better than we know it in our own galaxy, which is fun to think about. But what you can see is, you know, this, as I said, it's consistent with an ISM, what we see around these stars, or sorry, around these galaxies. Definitely more dense than M87, not as dense as a galaxy like our own Milky Way. The other thing I should note, which is interesting, is no other TDE surroundings have actually been observed this far out. So I wanted to put some other TDEs on this plot, but all of them are at, you know, 10 to the 5th or so still in terms of the radii that they're probing. So as the years progress, because as I said, this is sort of the first seminal TDE we could study in this detail, it's going to be really cool to see how this evolves, and this plot is going to fill up with all sorts of densities for these faraway galaxies that have shock waves going out from tidally unbound stars in the center of them. The thing to note is also this is going to remain visible as a source for a very long time to come. So this is a plot from the previous paper, and then I put the new radio observations here at different bands. This is the upper limit, and these are all detections. And what you can see is it's definitely fading fast if you're looking at the higher frequency regime in radio. But if you're going here in 1.5 gigahertz, I mean, this is, you know, 10 to the second. You're going to get a lot more PhD and postdoc projects, I think, out of this source as we continue to study it. The main thing is the peak frequency is definitely starting to move down into the lower frequencies. So our group actually just put in today was the deadline GMRT proposal, which is low frequencies. So we can hopefully start constraining the lower end of the low frequency light curve for this object. So that's going to be really fun to watch in the next few years, how this late time TDE evolves.
1.5 minutes.
Okay, cool. Yeah, so just to wrap up, for those of you who are X-ray fans out there, we did also take X-ray observations with Chandra, as I said at the beginning. 2 observations, 50 kiloseconds each. There was no emission detected, which is kind of a bummer, but the emission is definitely from the forward shock, and it's definitely just faded. So, I mean, it's been about almost 10 years now, or 8 years for this object, so it's kind of understandable that this emission would fade. However, we still can do some physics here. So as I said, I was talking about the equipartition, and you can study the magnetic field energy density to basically see how it works. So if you have equipartition, if electron energy density and magnetic field energy density are both 0.1. However, if you basically take those radio SEDs and extrapolate them, assuming 0.1, it really underestimates the X-ray fluxes that we're seeing. So it does look like if you fit epsilon equals 0.01 is a better fit. With the previous model in the last paper, it was 0.001, or 10 to the minus third rather. So we definitely are seeing, you know, it's with the reanalysis, we are closer to equipartition, but still definitely not there in terms of what's going on in the physics here. And just to wrap up real quick, some conclusions. I am writing up the paper. This is currently the actual conclusion section on the draft paper, but I think I probably need to update it because the referee is not going to like that. But yeah, this is a very exciting object. It's really, it's fading in the sky, but it's still going to be a benchmark for these TDE for many years to come. Still visible in the radio, no longer in X-ray, and that forward shock continues outward, and we're going to keep studying it for a long time to come. So thank you very much.
Thank you very much. Eileen?
Yeah, so hi everyone, this is Eileen Meyer. I'm going to be running the Q&A. So I see that we do have one question, so I'm just going to read these off as we have time. We may run out of time for your question, in which case you should contact the speaker via email. So the first question is from Craig Heinke. The ISM constraints are given in Schwarzschild radii. Are the results the same when put in parsecs?
Sure. So that's basically the reason the plot was like that, is because all black holes, of course, have a different size of radius for the Schwarzschild radius. So this is basically just a way to sort of make them all equal. Putting it out into parsecs, I have done that. We're probing out to about the first parsec and then a little bit is kind of the rough idea if you just take the radius in centimeters and don't account for that. But yeah, the reason it was Schwarzschild radius there was just to compare to like M87 has a huge black hole. So.
Great. Second question is from Edward Wright. What was the relativistic gamma factor early on?
Ooh, that's a good question. I'd have to look it up. I want to say it was, somebody else might know better than me. I want to say it was like 0.3 or something like that, but I'm really, honestly, I can't remember right now off the top of my head. I'm sorry.
Okay, do we have more questions? And I'll also remind the other panelists that they can unmute themselves if they want to ask a question. Okay, I will throw a quick one since I have the microphone. So my understanding is that now you're probing basically the sort of post-jet phase of this jetted TDE. So I was wondering, is there anything that you see that makes it look obviously different? Or to put it differently, suppose that this object had somehow been discovered now and we never knew that it had the jet. Like, would you say, huh, there's something weird about this?
Yeah. So that's actually a great question. At this stage, because we know the distance to this object, so as I said, we picked it up in VLAS, it's the luminosity is still like at least 1,000 times brighter or something like that. So wow. It's still a much brighter object. That said, if you found it in a radio survey, I mean, you don't know the distance to a radio source when you find it. So you would see this very slowly varying thing. And I'm actually wondering how you would discover a late time TDE just from radio data without, cross correlation and optical or something to see how far the galaxies are or something like that is also going to be needed.
Yeah, that's very, very interesting. Okay, thank you. Do we have any more questions?
We have two more in the Q&A.
Oh, I see them. Yes, sorry. I thought those were the previous ones. Okay, yeah, two quick questions. Matt Lister asks if there are any VLBI observations of this TDE or any others.
There have been some VLBI observations of them. I don't think there's really much detail that you can see at these distances. Maybe, I don't think there's been anything really from the VLBI, but people have tried it.
Yeah, I do know there's at least one that I'm aware of, but,
yeah.
And then Rodolfo Duran says, nice talk. Is there any evidence for polarization?
We haven't actually checked the polarization data. I think there is, but polarization gets tricky in radio, so we tend to not look in as much detail as we probably should. That's the answer.
Yeah, that's an interesting thing maybe to follow up on, I think.
Yeah, for sure.